Welcome, future pilots. Grab a seat. Today we're diving into an absolutely crucial masterclass for your flight training, high-altitude operations. You know, once you climb above 12,000 feet into that thin air, the rules of flying, and honestly, your own human biology completely change. I'm going to walk you through everything you need to fly higher, fly safer, and absolutely crush this section of your exam. So let's get right into it.
Okay, let's dive into this. Have you ever wondered why airliners bother climbing all the way up there? I mean, it's not just for the spectacular views, right? Flying high comes with some massive advantages. First off, the air density drops, which means less drag on your aircraft. Less drag gives you a higher true airspeed and a huge drop in fuel consumption. Plus, you get to cruise right over heavy rain and nasty turbulence for a buttery smooth ride. And heaven forbid you have an engine failure. Being up that high gives you way more time to troubleshoot and a much longer emergency glide distance to reach a runway. Oh, and your VOR and GPS signals, crystal clear. So yeah, climbing up into the thin air is totally worth it.
Here's our flight plan for today. We're going to cover 6 main waypoints: high-altitude characteristics and risks, essential oxygen equipment rules, oxygen supply system types, aircraft pressurization principles, understanding decompression, and finally, turbochargers versus superchargers. Get your notepads ready, seriously, because this exact structure is going to carry you straight through the exam material. Let's go.
Section 1. High-altitude characteristics and risks. Now, high-altitude flying isn't just about beautiful sunsets and smooth air. It comes with some pretty serious, invisible physical hazards. And the biggest danger up there isn't something you can see. It's the simple fact that you just can't breathe. And this brilliantly illustrates the core of the problem. A lot of people think there's less oxygen up high, but actually the 21% oxygen ratio in the atmosphere doesn't change at all. What does change is the pressure. At sea level, you've got 14.7 psi of atmospheric pressure, literally shoving that oxygen into your lungs. But by the time you reach 18,000 feet, that pressure drops in half to just 7.34 psi. Without that pressure, your lungs just can't force the oxygen into your bloodstream, which leads straight into a very dangerous condition called hypoxic hypoxia.
All right, pens out, everybody. You'll want to explicitly take notes or screenshot this chart right here. This is your time of useful consciousness, or TUC. It measures how long you can actually function, make smart decisions, and do your job as a pilot without supplemental oxygen. Just look at how fast your brain checks out as you climb. At 20,000 feet, you've got about 30 minutes. Not too bad, right? But push it to 30,000 feet and you literally have 1 to 2 minutes. And at 45,000 feet, you've got a terrifying 9 to 15 seconds. Hypoxia slows your reaction time, blurs your vision, and completely wrecks your judgment before you even realize what's happening. Section 2, Essential Oxygen Equipment Rules. Because of those scary biological facts we just talked about, the FAA doesn't mess around here. These regulations are strict, they are literally written in blood from past accidents, and I promise you, they are a guaranteed topic on your exam.
Okay, this is the most confusing part of FAR 91.211, so let's walk through it row by row. Write these numbers down. For unpressurized aircraft, if you're flying above 12,500 feet up to 14,000 feet and you're there for more than 30 minutes, the required flight crew must use oxygen. Push above 14,000 feet, the crew needs oxygen for the entire time, period. Go above 15,000 feet, and now everyone on board, including passengers, must be provided with oxygen. Now what about pressurized planes? Above flight level 250, you must have a 10-minute supply of oxygen for every single occupant in case of an emergency descent. Above flight level 350, at least one pilot at the controls must wear a sealed oxygen mask. There is a catch though. You can skip wearing it if both pilots have quick-on masks that can be put on in under 5 seconds with one hand. But cross above flight level 410 and that exception vanishes. One pilot must wear the mask at all times, no matter what. Make sure you've got those memorized.
Section 3, Oxygen Supply System Types. All right, so we know the strict rules. Now we need to know about the actual gear that keeps us breathing and alive up in that freezing, thin air.
First up is the continuous flow oxygen system. You've probably seen these. They're the simple masks with the little rebreather bag that drop from the ceiling for passengers. It does exactly what it sounds like. It pumps a continuous flow of oxygen into the bag. You breathe in the good stuff and breathe out carbon dioxide into the cabin. Now, this is a great, foolproof system for keeping passengers alive during a rapid descent. But for pilots, it's terrible. It wastes a massive amount of heavy, precious oxygen because it just keeps flowing out even while you're exhaling.
Next, we have the cannula system. This is also continuous flow, pumping a steady stream of air right into your nostrils, but it's way lighter and a lot more comfortable. Now, what's really interesting about this slide is the limitation. This setup is only effective up to 18,000 feet. Why? Well, think about it. If you have a stuffy nose or you just start breathing through your mouth, you're immediately sucking in the oxygen-depleted cabin air, and you are in serious danger of lowering your blood oxygen without even realizing it. Once you cross 25,000 feet, you need to step up to a diluter demand system. This is a much smarter, tightly sealed mask that works safely up to 40,000 feet. It saves oxygen by only supplying it when you actively inhale. Plus, it automatically dilutes or mixes 100% pure oxygen with cabin air based on your altitude, giving you the perfect ratio. Oh, and a quick pro tip for you future captains: trim your beards. If you have facial hair, you literally cannot get a proper airtight seal with this mask, which defeats the whole purpose. Now, if you're soaring above 40,000 feet, the atmospheric pressure is so incredibly low that even breathing 100% pure oxygen isn't enough to keep your blood saturated. You need the pressure demand mask. This beast literally forcefully pushes oxygen into your lungs. But here's the crazy part. Because the machine is doing the work of inflating your lungs, you have to use your own muscle power to force the air back out. Exhaling becomes incredibly exhausting over long periods. It's literally a full-body workout just to breathe.
Before we move on, let's quickly talk about where all this air comes from: the high-pressure oxygen storage cylinder. This aviation-grade oxygen is compressed to a staggering 1,800 to 2,200 psi, and it's 100% pure, moisture-free to prevent lines from freezing. During your pre-flight, check these carefully. Keep them away from extreme temps, and guys, absolutely no lighters or open flames anywhere near 100% pure aviation oxygen. The fire hazard is off the charts. Section 4. Aircraft pressurization principles. Okay, let's pivot away from rubber masks to the ultimate luxury and safety feature: pressurization. Instead of strapping gear to our faces, why not just bring the comfortable, low-altitude environment up with us? Let's move to the diagram and see how this builds. In a turbine engine, we tap into the compressor section and steal some of what's called bleed air. Now, this air is under immense pressure and is super hot, so we route it through a heat exchanger to cool it down and then pump it straight into the sealed fuselage. By continuously pumping air in and regulating how much leaks out, we can maintain a cabin pressure equivalent to about 8,000 feet, even when we're cruising at 35,000 feet. No masks needed and no painful ear popping. But holding that much pressure inside a thin metal tube surrounded by near vacuum conditions puts a massive amount of stress on the aircraft. Direct your attention to the cabin differential pressure indicator. This gauge shows the difference between the inside cabin pressure and the outside atmospheric pressure. As a pilot, you must monitor this constantly. If that differential gets too high, the airplane acts like an overinflated balloon, and you risk causing catastrophic structural damage to the fuselage. Section 5. Understanding decompression. So we've built this wonderful pressurized safety bubble. But what happens if that bubble pops? Let's shift gears to emergency procedures, because losing your cabin pressure is a very serious, very realistic threat.
Decompression comes in 3 flavors, depending on how fast it happens. First is gradual decompression. This is sneaky, maybe a faulty door seal or a tiny crack. It's so slow you won't physically notice it, which is why monitoring your gauges is absolutely crucial. Second is rapid decompression. The cabin loses pressure fast, but crucially, your lungs empty faster than the cabin does, so your lungs are safe from physical tearing, but your useful consciousness is dropping like a rock. Finally, explosive decompression. This happens in under half a second. The cabin pressure drops faster than your lungs can exhale, which can cause severe, trauma-level lung damage. If you ever hear a loud bang, see the cabin fill with fog, and debris starts flying, remember the golden rule. Secure your own oxygen mask first before you even touch the controls to start your rapid descent. You're no good to your passengers if you're passed out.
Section 6. Turbochargers versus superchargers. Let's transition to our final technical topic. Just like our human lungs, piston engines need dense air to perform. So, how do we force feed a piston engine up in the thin atmosphere? Let's look at chargers. Check out these awesome cutaway visuals side by side. They both do the exact same job, compressing intake air before it goes into the engine, but they do it in completely different ways. On the left, the turbocharger uses the hot, wasted exhaust gas blowing out of the engine to spin a turbine, which then drives a compressor. On the right, the supercharger doesn't care about exhaust. Instead, it is physically bolted to the engine and driven by a belt or pulley connected straight to the crankshaft. So, the crucial point is understanding the trade-offs here.
because you will definitely need to compare these on your exam. A turbocharger is incredibly efficient because it's recycling free wasted exhaust gas. But because it relies on exhaust buildup when you shove the throttle forward, there's a delay before you get the power. We call that turbo lag. A supercharger, on the other hand, is directly connected to the engine block. You push the throttle, you get instant power, zero lag. But what's the catch? It literally steals horsepower from the engine just to run its own belt, making it far less efficient overall.
Wow, okay, we've covered a massive amount of ground today. From the creeping dangers of hypoxia all the way to the mechanical guts of a turbocharger. So here's a question to chew on. Between the various oxygen mask systems and the cabin pressurization mechanics we covered today, what will be your most trusted safety net on your very first high-altitude flight? Think about it, and please make sure you review the notes you took today. Wishing you all safe flying, clear skies, and absolute success on your exams. See you in the air.